So let's quickly run through the various methods that obviously NOAA has to consider if they are getting into CDR research. We have already discussed these in some detail, so I'm not going to be dwelling on it too much. Direct air capture, of course, where you are using some kind of a system where ambient air is flowing through. It can be CO2 rich, but that's the relative term. And you have some catalysis or some binding operation chemically going on that leaches out the CO2 from the air, and then air that is quite depleted in CO2 is going to be put back out, and then you have a way of capturing it once you leach it out or precipitate it out and store it somewhere, and you have saturated filter is heated to 100 degrees C and CO2 is released in the sense that you have something here that is, let's say, absorbing CO2 or it's producing calcium carbonate or whatever. There are various ways in which these are being done, and that filter has to be recovered because you cannot keep on absorbing binding CO2 into the filter. You have to recycle it, so there are lots of details. So then there is also containment of extracted CO2, and you have to do transportation where you have emissions possible, so you have to do a life cycle analysis, and saturated filter obviously has to be then recycled back. Soil carbon and biosphere approaches, what we call nature-based solutions. So this is where you are trying to increase soil carbon, so agriculture, ground cover, mineralization, humification of carbon by microorganisms, all the natural processes that can also produce CO2, of course, but you are basically trying to enhance these natural processes so you can put soluble CO2 down deeper into the soil, and mineralization and immobilization of carbon by microorganisms so that you can ensure storage, durability of the CO2 that you are putting in. Carbon is absorbed by terrestrial and aquatic plants. We'll look at macroalgae, but blue carbon is going to basically depend on kelp, seagrass, marshlands, mangroves, other things. There's a lot of restoration work needed, but many of these kelp, seagrasses that can grow very fast can be harvested again and again with many co-benefits for oxygen, marine ecosystem, fisheries, aquaculture, and so on and so forth. Okay, so some details there, but you know that those are natural processes that are being perturbed in a negative sense by the warming. So warming can increase soil respiration, which means the CO2 release processes can get accelerated by the warming. So you're not only trying to put more CO2, but you're also trying to reduce warming, so you can have a virtuous cycle that the natural sinks also begin to get stronger again. Macroalgal cultivation for carbon sequestration. So I didn't include this for others, but anyway. It happens in the ocean, typically in the open ocean, so intentional biomass sinking. So you are somehow going to go in a ship and induce macroalgae growth, which can grow pretty rapidly, and if you can find a way to sink them out, then essentially you can put it down into the deeper ocean where it becomes part of the sediment and can stay there for very long time. So durability and leakage can be taken care of. Okay, so you have blue carbon, which we'll come back to in a minute, but you also have macroalgal cultivation, which is ocean CDR. Okay, so there are other details here. CO2 emissions are not completely removed because your operation will produce some. So you have seaweed farming, and seaweed has, depending on which seaweed it's also shown to reduce methane emissions from cattle in some cases, or it can be used for food in many cases, and so on. So you have methane and CO2 emissions happening there, but you obviously want additional sequestration, so you want to store biomass in the seafloor and take out more CO2 than you're emitting methane and so on. So you can also harvest seaweed for the markets, and processing food, fuel, fertilizer and compounds can be produced from the algae as well. I'm not reading these things here in terms of technological readiness, estimated cost, scale potential, duration, and NOAA potential, but obviously NOAA is trying to pitch it as their strength, so they are very optimistic about many of these things as well as their ability. So NOAA is the National Clearinghouse for monitoring spatial planning for macroalgal aquaculture, as we already said. It's a nice hydroponic 3D farming kind of system in the ocean, right? So people are also doing that for aquaculture, growing shellfishes and so on. Alkalinity enhancement, I've discussed in some detail elsewhere. So ocean waters are alkaline. Depending on the alkalinity, it has this buffering reaction where it can take up CO2 and put it away and doesn't get saturated and so on. And you have CO2 uptake, so you have minerals that are mined, crushed and dispersed. So you have accelerated weathering potentially happening, which can then wash into coastal regions, and CO2 uptake can happen as well. But alkalinity enhancements are artificially driven, which we have discussed elsewhere. People have issues with it. Not everybody believes it, but the potential and duration are so high. So readiness kind of low to moderate. So some experiments are being done and they will continue to be done. Scaling up, what is the scale potential is moderate to high, 1 to 15 gigaton CO2 per year. So this is something that will happen, and here is more information on this. You have electrochemical approaches. So ships and pipes release alkaline seawater into the surface, raising pH, and ocean has a buffering ability to try to keep pH at a certain level, which it has done for millions and millions of years. We can use that natural ability to bring down or raising pH and then absorb CO2 to balance the pH. So neutralizing acids are put in here. So this is approach one, separate seawater into acid and base. So there is a seawater intake system, and you release it back into deep ocean in the bottom right. Approach 2 is transport acid to the market. Approach 3, sequester acid in the deep sea, and so on and so forth. So all these are obviously pilot stages, lab experiments, and there will be some open ocean experiments. I haven't seen any results yet, but you can follow up to see if people are already doing that. Direct ocean removal, so you are trying to put directly CO2 into the ocean. So you have electrochemical treatment of seawater that is powered by renewable energy, just for being more mindful about reducing emissions from this operation. And then you store extracted CO2. So you are doing direct ocean removal, just like direct air capture. So processed water depleted of CO2 is expressed here once you remove CO2 from the water. So CO2 uptake is happening by natural processes. So you transport to coast for commercial usage of extracted CO2. Believe it or not, even though we have a lot of CO2 increasing in the atmosphere, industrial users often face shortages of CO2 they need for their processes. So containment and shipping, CO2 emissions, transport to market. So just for good completion's sake, the infographics have all these details, but the reactions are important. Safe pH changes less than equal to 0.4 units. So acidification is going from bicarbonate plus H plus to carbonate and water, and basification is happening with something like sodium hydroxide, NaOH plus CO2 to produce Na plus and HCO3 minus. So you have the processes that are sustained. So this is bipolar membrane electrolysis that allows acidification of seawater to remove CO2, and its sequential basification before release to the atmosphere to absorb more CO2 from the atmosphere. So again, technological readiness is low to moderate, but duration can be high, and cost can be high, as we saw, and NOAA has moderate potential impact on that. Ocean fertilization we have discussed before, where there are certain nutrients that are in demand. So if you add them like iron, you can drive additional photosynthesis, and there are some controversies about whether that really produces export, because if you drive additional photosynthesis, you have to make sure that sinks, similar to what we argued here, right? So you have to sink it out. So intentional biomass sinking has to happen, and some experiments done before have shown that photosynthesis does spike, but then it's recycled right back and not much export happens. So there are some details that have to be worked out. Nonetheless, more biological productivity can happen and increased carbon storage can happen. Nutrient enrichment is done, which produces some emissions, so life cycle analysis has to worry about that. There is some complicated looking equation here, so you can see how that is driving CO2, nitric oxide, and other compounds, including water. So essentially, it's a fairly straightforward theoretical calculation, and ships have gone and done it. They do enhance photosynthesis, but as I said, ensuring export is always critical. Artificial upwelling and downwelling, we have seen this also before. So transport of high CO2, low oxygen water up to shallower depths where you have enough light and nutrients to drive photosynthesis. So natural sinking of biomass pumps cold, nutrient-rich water up to the surface to stimulate biological productivity. So enhanced natural process, energy utilization, and carbon outgassing, important considerations. This is being tried around Hawaii already, I think. Maybe at other places you can look up. You can also do artificial downwelling, where you pump warm surface water down to the deep ocean, enhancing carbon export via physical mixing as opposed to biological processes, bringing CO2 back down. So experimental process that requires more energy than upwelling to cause downwelling, and engineering hurdles exist here. You are using various natural processes to pull up water, whereas here you are pushing water down, buoyant water down. Here you are bringing up heavy water up, and CO2 increases with depth because temperatures are colder, pressure is higher, solubility is higher. It's like a Coke can. Keep it cold and sealed because you want it to maintain the fizz. If you open it, it begins to leak, and so on and so forth, right? Coastal blue carbon, again, something we discussed already. You have basically seagrass bed, mangroves, salt marshes, etc. Some carbon is being imported from high watershed areas, so you are sequestering new carbon, mixing with the old carbon. Carbon is stored for long time scales in biomass and sediments. So sometimes methane is emitted to the atmosphere through methanogenesis by microorganisms, which is very natural when you have high biomass that is not being grazed by some of the zooplankton or others, and then you have some bacteria that are producing methane when they respire the biomass. Some carbon returns to the atmosphere through respiration by microorganisms and vegetation, but you all obviously want to make sure that carbon is absorbed by coastal blue carbon ecosystems through photosynthesis that is put away. So you want to put away more CO2 than obviously this is like afforestation on land, but these things don't burn down. They sequester 3 to 10 times more carbon than land forests, and so on. So they also increase oxygen, habitats, fish productivity, aquaculture, etc. Okay, ecosystem recovery. It's something that is holistic. So NOAA is a national leader in coastal blue carbon monitoring, conservation, and restoration, as we said. It has moderate technology readiness. This could be basically recovering ecosystems that have been damaged by warming, by circulation changes, by acidification, and so on. And NOAA's potential impact can be high here, but estimated costs are reasonable. but scale potential is low and duration is also low to moderate. So it can help to be part of the portfolio and overall reduction up to 2100, by which time hopefully you have all the other technologies fully ready to go, and so on and so forth. Okay, so we'll come back and look at next steps to, well, let's do this here. NOAA needs to develop advanced mass balance models for marine biomass connected to connected by food webs and in aquaculture ecosystems to determine the scale and potential for wild and farmed blue biomass to enhance carbon sequestration. That's ecosystem recovery. Consider carbon sequestration and storage as a key benefit, target, and management priority of current and future marine protected areas and farms, including identification of key habitats or marine processes that could substantively increase atmospheric carbon sequestration, establish carbon sequestration measurements at farms and key sentinel sites within NOAA National Marine Sanctuary System, National Estuarine Research Reserve Systems to identify early changes in carbon pools and fluxes to ensure that duration and storage and leakage are being monitored. Research the interplay between key restoration activities such as opening rivers, reconnecting wetlands, restoring shallow corals, and rebuilding shellfish populations to understand the net efficiencies of methods that both release and sequester carbon, so that overall you are sequestering even if it's for relatively shorter periods. Okay, so this is just a summary table of the same thing, looking at all the technologies and what the co-benefits are. So fertilization, nutrient robbing, toxic materials exposure, modification of pH and alkalinity, increased ship traffic, fishing and ship obstacles, habitat alteration, and introduced species. So each of these approaches have other impacts in terms of these that are potentially unintended and unwanted. So you have to be obviously aware of those and track them. That's where quantification, monitoring, reporting, verification come in. Okay, so let's come back and look at the next part, which is the proposed development of CDR research and coordination in terms of the next steps. So it's a complete report because NOAA is really trying to pitch itself as the potential lead agency for CDR research, carbon dioxide removal research. Okay, let's keep that in mind.